Welcome to General Chemistry 2 Laboratory. This week we're going to look at an experiment in which we do qualitative analysis. Qualitative analysis is classic chemistry. It's wet chemistry, so we're going to do a number of reactions. And so we're going to learn how to perform qualitative analysis on a semi-micro scale basis, so small quantities of materials. And it's also going to help to bring back rules from chapter 5, the solubility rules. And so we'll use solubility to perform our analysis. And then we'll also learn about some things that form in terms of wet chemistry called complexes. We've discussed them in a number of labs, and they form with certain cations but don't form with other ones. And so it'll allow us to do a separation of ions with wet chemistry. So the true purpose of this experiment is to identify these ions. The cations that we're going to be looking at are sodium, magnesium, nickel, chromium, zinc, silver, and lead. And then the anions are nitrates, chlorides, iodides, and sulfates. So in this experiment, what you're going to do is you're going to actually do reactions with these ions. You're going to know what the ions are, be able to visually see, make notes, and build a set of data, all right? And then we're going to give you two unknowns, okay? And then you're going to be able to, from the reactions that you've done, identify what the unknown ions are that we've given you. So anyway, the anions, nitrate, chloride, iodide, and sulfate. And so we could do this by a number of different methods. One of the first things that comes to mind as an analytical chemist is spectroscopy. And there's a number of forms of spectroscopy that we could do to look at these ions. And we could just look at their spectra, those types of things from emission, or we could look at absorption at particular wavelengths. And so we've been working on these methods, but we're not going to use that type of analytical method today. Or we could actually take these ions and put them in a HPLC and do ion chromatography. We could separate them, identify what they are with standards. This is an example of a separation of lithium, sodium, ammonium, potassium, and magnesium ions. And so you can see how they're separated. And then the area inside of each one of these peaks is representative of the concentration that's present. Although detectors respond differently to different ions, but we'll learn about that in instrumental. But we're not going to do it that way either. You take instrumental chemistry, we'll work on that there. But instead, we're going to do reactions, okay? And making sure our pH is appropriate. And so we're going to look at reactions with color and solubility. And so anyway, so those are the things that we're going to use to do our separation today. This is a separation of some of the ions that we're using, actually silver and lead, and then the mercury ion. And so this is a group 1A cation separation. And to do this, we do wet chemistry. And so if I add HCl to this group, right, then they precipitate, right, with as a solid, and then we can centrifuge, and any of those could be present, right? Now, to do a separation then, what I would do is if I add hot water, and if the solid dissolves, then the supernatant may contain lead. And to confirm that, I could add chromate, and if I did that, the lead chromate would precipitate as a bright yellow color. So that would be a confirmation. If the hot water didn't dissolve it, then it would either be the silver or the mercury, and so I can add ammonia. And if I add ammonia, a gray precipitate forms, then add HNO3, and a white precipitate indicates silver. And so in that relationship, then we can separate the mercury from the silver. And so at the end, we know which ion is present. you're going to do the same thing except for that set of ions we saw on the previous slide. And now you notice our list is more expansive, so you're going to have more trees of reactions to make this happen. And so in fact, the reactions that we're going to do is we're going to begin every experiment by adding hydroxide, sodium hydroxide, to the metal solutions. And well, when I add it to magnesium, we precipitate the magnesium hydroxide. We also make the nickel hydroxide. We make the silver hydroxide. And we also would make a chromium hydroxide, a zinc hydroxide, and a lead hydroxide. Now, those are, well, in fact, we say hydroxides are insoluble. But basic hydroxides, even if I add more sodium hydroxide, they remain the hydroxide, so they would remain solid. But the amphoteric hydroxides do something really cool. When I add the excess sodium hydroxide, right, then what you notice is the chromium has 3 hydroxides, it adds a 4th. And when it does that, it becomes charged -1, and so the chromium hydroxide solid redissolves and disappears, okay? And it goes back into solution. The zinc hydroxide, right, does the same thing. It goes from 2 hydroxides to 4 in its complex, and because it's a -2, as does lead in a similar reaction. So I can initially precipitate it out with a limiting amount of hydroxide and get the amphoterics to redissolve. And so now I have separated the basic hydroxides from the amphoteric hydroxides in the first step of a separation. So if I have one of these or one of these, then I would be able to distinguish that. Now there's other things like chromium and nickel, they both have distinct colors. So the solutions will have colors, and so I want you to make those observations so I could identify them from the others. And the next part of this is I'm going to start over again and do some reactions with ammonia. And when I put the ammonia in, then I form ammonium complexes. So the nickel ammonium +2, a zinc ammonium +2, and a silver ammonium plus. And so those will form complexes and stay dissolved. So I can find when I have those ions. Now, other ways, once I have my initial reactions and I made my observations and built that scheme, then I also want you to do a set of, we call them stability sequences. Now, if I'm looking at a stability sequence, I start on the left-hand side and go to the right. And so if I have silver hydroxide solid in a solution, and I add sodium chloride to that, then the chloride will displace the hydroxide, and my precipitate will change. If I add ammonia to that silver chloride, then it will actually go from solid back into solution with the charged complex. So remember, things that are charged are dissolved. And then I can force that silver to precipitate back out by adding silver iodide. And so this is the end of my stability sequence. Now, if I start with silver iodide and I added ammonia, then nothing would happen. I would just have the silver iodide. I can't go backwards in my scheme. I can only go forwards. And so these reactions can be useful if you think you have something. For example, you think you have silver and you think you have, for example, silver chloride, then you can walk through this to the end of the stability sequence. So I want you to perform these for silver, lead, zinc, and nickel, and so then you can utilize those to confirm what you think you have in many cases, okay? So your goal really is to solve a puzzle. We're going to let you build your own key to the puzzle by doing reactions. You're going to know what they are, and then I'm going to give you unknowns, and you're going to use your key that you made to determine the identity of the unknown. So this is actually a really fun lab, in my opinion. Some helpful documents for you would be these next 2 pages, which are from chapter 5, the solubility rules. that we learned then, because all of that in terms of ideas is in this scheme. Now, it doesn't explain the complexes, for example, with the hydroxides that form with your amphoteric metals. All right. So when we're talking about precipitation, I think most everyone in here already knows this, but this is a precipitation. It's barium chloride in solution dropping in sodium sulfate, and barium sulfate is insoluble, and so it precipitates out. The white solid there is considered a precipitate. Now, just because whenever, in fact, this is a good point, whenever I have cloudiness in my solution, right, the turbidity of the solution changes, it becomes more turbid, then that's an indication that a solid is forming. Now, if I have color, but I'm still transparent, there's no turbidity, then that means it's dissolved in solution. So you guys are looking for cloudiness in your precipitation. Now, sometimes the precipitates are very dense and they will go to the bottom and your solution above that will be very clear. Or we can actually put that into a centrifuge and push the solids, which are more dense than the liquid, to the bottom, and then that allows us to decant, and we have the solution on top or we have the solid on bottom to do more chemistry, and that will be useful when you're doing the two cations. And so when you're doing or working on that. This is another precipitation. This is showing silver and chloride precipitating, and so we have silver chloride solid forming in the container. So just what to watch for. All right, those are the things to watch for. Now, before you can begin your lab, there are some questions that you're supposed to answer. All right, and the first one says your unknown compound doesn't dissolve. What should you do before you attempt the stability series? Well, the first thing to do would be to start with hydroxide. Okay, add sodium hydroxide, see if it is amphoteric and forms a complex. So you put in that excess, put in normal, and then put in the excess. And so you start just like you would with something that doesn't dissolve. All right, it's possible that if it were, for example, lead chloride, that you could heat that and it would dissolve. All right. Now, the second question says your unknown green or purple compound dissolves readily. What do you already know? And, well, if it's green or purple, then it's nickel or chromium. Okay, and you've seen that and you've put that into your key. Okay, and then how can you tell the difference between the two cations in your own unknown? What should you start with? How do you begin once you're doing your unknowns? And the question would be to begin the same way you began making your key. And the answer here is the same as up here. Don't panic. Add sodium hydroxide. Make observation. And then go on and follow that through. All right? Your unknown white compound dissolves readily. What should you do first? Add sodium hydroxide. Okay? So start at the beginning and work through that step by step, even if it doesn't dissolve when you start to do your unknown. All right. The results for this, you actually have 2 weeks. What you want to do this week is make sure that you get all of the known reactions done. You can even take photographs with your phone if you would like to document that so you can go back over. And remember that in 2 weeks when you're working to find the unknowns, that you can actually go back and make the compound that you think you have and see if it behaves in the same fashion. So your chemistry doesn't stop because you've made the key. You actually can go back and redo a key section to make sure that that's the compound that you have as an unknown. So you do confirmation chemistry, all right? Everything should be first recorded into the worksheet. And so there's data tables through the observations that I put in there for you. But then there's a set of summary tables at the end of the lab. Be sure and fill out the summary tables based on the information that you recorded while you were observing. Make good observations. We're going to grade on observations this time, so be aware of that. And safety glasses, all right? There will be containers. These ions cannot go down the drain, and so there'll be containers for them in the back for you to put them in. So use appropriately marked containers for the materials in this lab. All right. I'm looking forward to seeing you in lab next week. Good luck on the quiz, and